Okay, guys, we're gonna enter in the last part of our ranking analysis cycle. The only thing that we're missing is the technical law analysis for ranking cycles. Before we start, let me just try to remember the equation that we have for efficiency and let me change the color. Recall that our efficiency was defined as the network divided by the heat that we add, and everything that we have done has worked to increase the network. But if we, which of course will increase our efficiency, but if we want to increase our efficiency, we can also reduce the amount of heat that we are introducing. And since this power plant could be just as a one big system, remember that we have Q in, work net, and Q out. Everything that we try to do in order to reduce this Q in will increase efficiency, but cannot come from the outside, should be from the inside. So we should have a way of reducing the amount of heat that we are introducing, but using the means that we have inside the system. Okay. Secondly, we can recognize in this diagram that the temperature difference that we have, that this scale is temperature, and temperature of the reservoir should be higher even than this one, right? Because we need some heat, some temperature difference in order to produce the heat flow. So let's assume that this is RTH, and in this case this will be RT low. So this big delta T produces a lot of entropy, which we're gonna discuss on chapter 8, that produces a lot of exergy destruction. So we would like to minimize that. How do we do that? Well, we know that we have here, point out, we have here at this point, this turbine inlet. We have superheated vapor. We expand it, and we already know, because we did it in the reheat cycle, that we can extract steam. It's not a big deal. Maybe we have to take some considerations to avoid leakage, but we can do that. What if we take that highly energetic vapor at high temperature and use it to preheat part of this water? It would only help us if that loss of work that we are getting, because we have mass flow rate producing work, and if we extract some part of that mass to reheat, we're going to produce less work. But if that loss of work output from the turbine, it's less than the amount of heat that we are saving, then we are increasing our efficiency. So that's the idea. So that's basically what we're saying here. We're gonna use part of the heat of the steam that we're using to expand to produce work. We use part of that work, of that steam, to preheat water. And we can have two types of feed water heaters. One is an open one, and second is a closed one. Both are basically heat exchangers, and we're going to discuss them in more detail right now. So let's start with the open feed water. This is exactly what you have in your book, and we're going to be doing a closer analysis to this. In the open feed water here is just basically like the top of, in any bath, top bath. You have hot water, you have cold water, and you mix them until it gets to the desired temperature. So we have the same. Here we have all the mass coming to the turbine, and after a while we extract a little bit. So we extract here. We have mass flow rate flowing, and we take that steam to this tank. The rest of the steam continues expanding to give us some work of the turbine. But now this work of the turbine will be composed differently, and we're going to check how. So now we have less. This Y that we have here is the fraction of mass that we extracted. That's if we have 100% here, 100% of mass flow rate flowing through the tubes and entering the turbine, just one small fraction, let's say 10%, is extracted. If you extract 10% here, we're going to have 90% here. The total should be conserved. So we expanded previous work, then condenser, similar to anything that we have done in the past, and then we have a pump. This pump is not going to increase the pressure onto the boiler pressure, but it's going to increase it to the pressure of the paper that we extracted. Okay, this pressure here, pressure 6, is greater than pressure 7, which is the extraction, the condenser, but is less than pressure 5, which is the pressure of the boiler. So here pressure is equal to pressure 6 because we are mixing these two tanks. So they should be at the same temperature, at the same pressure in order to mix them together. Otherwise we cannot do that. So this pump will increase the pressure until the open feed water here. We mix them, and the idea is that just like this, we would like the quality to be 0. That means liquid water. We would like to have this quality 0. Recall that otherwise, if we have quality greater than 0, we could have problems with the pump because our pump cannot manage two phases. So basically, and here we have all the mass again together, so we can pump it to the boiler and the cycle starts again. Basically the goal, let me change. The goal here is change again, is to find out this value of Y, because there's only one value of Y, of Y that will make this true. Let's say that we have our Y is bigger. Just assume for the argument that the optimum Y is 10%, just for the argument. If Y is greater than 10%, then we start to boil. If Y is less than 10%, then we have still subcooled. So the goal is to find the proper value of y so we can have saturated liquid mainly here. Okay, so we can manage. Again, if we have more than that, we will have problems with still starting to boil, so we have some bubbles, and our pump would not be able to pump. If we have less, we still have to cool, and we remember that we would like to avoid that subcooling. In this case, just to reduce the amount of heat that we need to provide. Whereas the benefit, you can see it here. If the original cycle, we're trying to do this. So is all this heat that we are saving that reduces the amount of heat that we are introducing, and because of that, remember that we are just reducing this Q in, we are increasing our efficiency. Okay, before we go to this part, let's do how do we compute this value of y? Okay, so we start with the open heater, and we're gonna start doing by doing a small diagram of the heater. As we described, it's just a tank, and in this tank we are gonna have two mass flows. We're going to have coming from the turbine we have a mass flow rate, just a fraction that we extracted at the enthalpy that the paper had when we extracted. Coming from the pump, this is the feed water. It's the water we would like to heat. So we have from our mass flow rate, the remaining vapor, we extracted y, the fraction y minus y is what is left, and this is the enthalpy. We can see we are consistent with the numbers that we have here. Okay. This tank should be at the same pressure, and this tank is at pressure C. It's the same pressure that this paper has because we extracted from the turbine. And what we do is we calculate this fraction that we extract. So we have this at pressure 3 equal to pressure 6, and we would like to have saturated water. So at the exit we have the mass flow rate, the complete, because we now join both times the enthalpy 3. So at the end, our energy balance, if we drop all the let's write correctly, we have at the inlet, we have two inlets. This is what comes, the energy associated with the vapor that we get from the turbine plus the energy associated with the fluid that comes from the pump. And sorry, this is this is 2. Oh. And at the end we're going to have mass flow rate H3. We can see that we can drop all the M's, so at the end we're going to have this. So if we solve for y, we're gonna get and I'm sorry, this is H2, and then we have I'm committing the same mistake over and over again. So we have H2. So this is the fraction of vapor that we need to get in order to have saturated liquid at the exit of the mixer, which is at P6. And only this fraction will get it. If we extract more from the turbine, as we said in the previous slide, we'll start to boil the water. If we have less than this, we'll have some cooling. We can see here that we have two pressures. This is the pressure of the extraction. This is the boiler pressure. I think that here is very clear. So this is the way that we are gonna compute this fraction y. And again, this is for an open system, for an open feed water heater. Sorry. So let me just write, this is for okay. Next we're going to discuss the closed feed water heater. Now for the closed water heater, we're going to change your ink so we are not confused. So we are going to talk now about the closed feed water heater. And we'll start again with a small diagram. The main difference between the closed and the open is that the closed, the fluids are not mixed. So we have this gas, this vapor comes from the turbine. So again, we have the fraction that we're extracting and then the that it carries. We're using exactly the same nomenclature, and what we are saying is instead of having this, we're gonna have an extra one, so we're going to consider this as a state 8. Okay, so this is sorry, we have this will have same mass flow rate, same fraction, but now H8, and this comes from the pump. So it has the mass flow rate, the remaining fraction, times H2, and at the end we have mass flow H3. Now we have two differences here, two main differences, and I'm going to point out this with red, that heat transfer occurs inside the heater. So we have this heat transfer. The thing is that ideally we will need a delta T here in order to maintain this heat transfer. So there are two ways to assume this. The first one will be that two ways to deal with this situation, and the first one is that we know delta T. We call this the approach. And delta T could be, let's say, 5 degrees. So in order to pinpoint this, we will know that this delta T should be maintained at the end, right? The second one, and along with this situation, we could say that the purpose of all this is that we don't want to have a mixture here, so we would like state 8 to be saturated. That means and pressure is equal to pressure 6. You can see that we don't have any pressure mixture here because now they are separated in different tubes. Okay, with that in mind, we know if we know the pressure and this quality, we know as the saturation temperature. Along with this delta T, we know we can find 2-3. That's the first way of doing it. Second way will be assume that delta T is 0. In that case, we're going to assume that T3 equals T8 and T8 is T sat and P6. Okay, this is more conservative. We know that this delta t cannot be 0, but with that we can compute these two values. So at the end, the only problem will be to find out y. And we can start with an energy balance similar to what we did in the closed system. And the entrance we will have the mass flow rate, the fraction, H6. This is the steam that comes from the turbine plus mass flow rate, the fraction that we are remaining, H2 that comes from the pump. And what is exited the heater is the mass flow rate, the fraction that we extract from the turbine, H8, plus mass flow rate, the fraction remaining, H3. We can drop mass flow rate and solving for y, we can get sorry, we need to move this. This is minus H8 as H3. Again, with this y, we can assure that we have saturated liquid here. If delta t is 0, we know that this will be the edge of the fluid. Since liquid is incompressible, we remember that if we don't have subcooled tables, we're going to use saturated properties at the temperature of the mixture, at the temperature of the fluid.